Let me just start to start my talk with the outline. Very briefly, I will talk about our approach to the study and the goals that we tried to achieve. I will describe the test set that we used. Then I will talk about the tool reports and our analysis. And I will point out problems with the analysis and conclude with future plans. So, but first, unfortunately, I have to put this slide, and this is important for if you take anything from this talk, it should be this. In particular, our analysis of the tool reports was incomplete, simply due to the lack of resources. We had some problems with the criteria for analysis, and I'll explain them later. There are outright mistakes in our analysis, and also the use of the tool in real life is somewhat different. Users write special rules, they suppress false positives, and they learn to write code in certain ways that minimizes tool warnings. And also, there are many other factors besides warnings in particular lines of code that we didn't consider. So to say this caution is not to use our analysis to rate or choose the tools. So what questions we tried to answer? First, what weaknesses exist in real programs, and what do tools report for the real programs? And we focus on tools that work on source code, and we focus on defects that may affect security. Some tools may focus more on the quality issues, and that wasn't the focus of our study. Our goals of this study is to first of all, enable empirical research based on large test sets, which we produced. And second, encourage improvement and adoption of tools. And there were some problems with this from this study. So, but again, I want to emphasize this. The focus was not to choose the best tools, was not to rate tools. So a good way to describe the study briefly is to give a timeline that we used. So we chose the test programs, 6 test programs, 3 in C and 3 in Java, and I'll describe them in detail later, and provided them to tool makers. Tool makers ran their own tools on the test sets and returned the reports to us. Then we had 6 weeks to analyze the tool reports, and in retrospect, that was clearly was not enough. And then the tool makers had 2 weeks to critique our analysis, and we updated our analysis based on the critique. And again, here there are this 2 weeks there, 2 weeks here. It turned out to be too little time based on the amount of work, and this caused problems in the analysis. I will describe it later. Then we met at the static analysis workshop in June to discuss the result, the tool reports and our analysis, and we intend to publish the data in December. So now to talk about participants. There were 9 participants, 9 tool makers, and I'll list them now with some details. So aspect security, you would say, oh, that's not even a tool. Yeah, that's right. But they still they produce data in the format that's that we requested. So that we said it's okay. They did, of course, manual review, and they only did the static part, the static review. The checkmarks CX suite. Flow Finder, my colleague Romain Gotcher ran it. Fortify source code analyzer, Grammatech code sonar, DevInspect from HP, They have a hybrid tool, but they used only static part of the tool for SATE. Soft check inspector for Java, find bugs, and Veracode security review. Again, it's not, strictly speaking, not a tool, it's a service company, but they use tools internally. And so each of those 9 participants provided reports in the required format. So if you can return reports in the required format, then you can participate in this study. And it was interesting to see different kinds of participants because they find different things. They look for things differently. Now about the test cases. We had 2 tracks. For C track, we chose this Lighty, Nagios, and Name. And for Java track, we chose DSpace, MVN Forum, and OpenNMS. All of them are open source programs, and we try to choose them so each one has some aspects relevant to security. This is the size of the programs. It ranges from about 20,000 lines of code to about 130,000 lines of code. The Java programs are somewhat larger, mostly due to the nature of the language. Some properties of the test cases. 4 of the programs have web interface. 3 of the Java programs and also Nagios. So those are interesting security errors to look at, but they may not be focus of some of the tools. The tools that may focus more on other types of applications. We found that the design was decent, but not much attention in some of the test cases. Not much attention was paid to security. We also chose to take stable versions of the software, and that was somewhat of a mistake because the developers of the test cases would have preferred us to choose the latest version because the feedback would have been more relevant. And OpenNMS specifically had a lot of warnings, and that biased the study and caused us many problems. In order to do the study, we had to have some common format. So we produced one sort of lowest common denominator of the tools that we looked at. So, of course, the tool for each weakness, it has to report one or more location. And so if it's just one location, then it's that. Otherwise, it could represent a trace in the program. It reports the name of the weakness, and we also encourage tool makers to report a CWE ID because that simplifies comparison. We ask them to rate the issues on severity from 1 to 5, with 1 the highest. Probability that the problem is true positive. Original message from the tool, and there was place for other annotation. I'll touch on it later. So to describe some of the problems, format was not expressive enough. It did not support, for example, multiple traces. It turned out to be underspecified, and it took us 3 weeks to convert tool reports to the format that we wanted. There were some little details. Some weaknesses may not map to CWE IDs well, and we had a lot of weakness names that we had to somehow reconcile. And severity classification is very subjective. Tools use different things to rate their weaknesses. So what the tool makers did, they converted their tool reports to our SATE output format. They described the environment in which they ran the tool, so which operating system, some other detail. Some of them also provided analysis of their reports, and some of them provided critique of our analysis. That was very helpful, but unfortunately, we didn't give them enough time to do that, so some did not. just due to the time constraints. And want to note that we did not provide them any context for running the test cases, so they could assume the worst case of environment. Now about the tool reports, they mostly handled the code well, which is not trivial for the size of programs. There was some very interesting analysis. There was a total of almost 48,000 warnings, so that was huge, and it caused us a lot of problems because we didn't have enough resources to analyze it. It just by simple calculation, it takes you can come up with man years to analyze everything thoroughly. And there were about 100 different CWE IDs in the reports, and 291 different weakness names. Of course, some are very similar, so in some cases it was easy to combine, to understand that they are really referred to the same weakness type. So now, this is the division of warning by test case. And one thing to note is that this very big part in the bottom, it's for OpenNMS. So this skews, this biases the results of any analysis that we do because of so many warnings there. Now this is a division of warnings by severity as assigned by the tool. So severity 1 and 2 are the subsets that we decided to focus on simply due to the lack of resources. And that, of course, causes a lot of problems because this is fairly, well, even in the lower severity issues, there are many different cases, many interesting cases to consider. So partly to make a better presentation and partly to simplify our analysis, we also divided the weaknesses into 3 broad categories. Based on security relevance, this is strictly based on the weakness name and CWE ID. So let's say in the high category, we put all XSS warnings, SQL injection, other input validation problems, race conditions, buffer errors, authentication, authorization, and so forth. So these are types of weaknesses. Within those, there may be some warnings which don't really qualify as high severity issues. This is just based on the weakness names. So we had also medium and low categories. And even in the low categories, there are some interesting cases. It's just that in looking at the weakness name, we thought that we can put it there. So this is a division of warnings by weakness category for the Java test cases and for the C test cases. And of course, in case of the C test cases, we subtracted the flow finder reports. The reason is that we had certain difficulties in qualifying the weaknesses from this tool in which category we should put them, so we decided to subtract them. And I will use this weakness category, will refer to this weakness categories later. So this is the warnings for the high security relevance category for the Java track. This has a fairly large, XSS is a big part, is about half of all the weakness reports in that category. And there are SQL injection, command injection, other types of issues reported by the tools. This is, by the way, these numbers are just the number of raw warnings produced by the tools, so some of them may refer to the same weakness. I will talk a little bit about it later. These are the warnings for the C track, and there is a prevalence of buffer errors. This is maybe again due to the way we classified them. So buffer errors, buffer overflows, and related stuff. And again, this is without the reports from Flow Finder. Some general ideas about, because we had a company that did a manual analysis here, we can have some ideas about the comparison here. This is again just qualitative. So tools are fairly good for XSS, types of injections, and memory problems. They are okay for some classes of authentication errors and information disclosure. And you need human help for the types of problems where you have authorization problems, logic flaws, some complicated cases of other weaknesses. But of course, tools can quickly report hundreds of weaknesses for some classes, so that's of course an advantage of automation. Now, analysis of tool reports. This is how we felt. I need to tell you about what kind of, about our criteria and also what kind of problems we have. So first, you have to classify whether it's false or true positive, and it turned out not a trivial problem at all. Then severity, in our opinion. Sometimes we would assign a severity to a weakness that is different from what the tool assigned. And I give an example where input comes from configuration file during installation. So we would downgrade the severity to 5 because it's not really a problem, but tool doesn't know about this because it doesn't have the context. And we also try to associate the warnings that refer to the same weakness. And due to lack of resources, we focused only on severity 1 and 2 issues and missed a lot of important issues. So about the false or true positive, we assume that tool doesn't know about context or environment, but we expected that the tool understands the code. So if you, for example, if you report a particular problem within a function, let's say, but the function is called everywhere correctly, so it's not really a problem, then the tool should not report this kind of problem. But this analysis turned out fairly complicated. And there are cases where, for example, a tool report is true, but it may not be relevant. We basically don't care about it. In that case, it's not, if we just classify it as true positive, then this is a false negative for another tool. So that's obviously a problem. So we have to have a category true, but we don't care. And there were some other problems which we had with this classification. Also, the criteria, our analysis depends on the type of weakness. In some cases, for some types of weaknesses, it's really hard to say that this is absolutely not a problem, even though I can have no idea of what can be the problem. And so for example, in course of this analysis, we wrote a document just to try to classify XSS problems. This turned out often subjective, which is of course a big problem, and to conclude, we need much better criteria. This is so just with these caveats to go to what we evaluated. This is the total warnings, and we looked in any way at a bit under 6,000 warnings. And so we found that we tried to associate the warnings that refer to the same weakness. So those that don't, those warnings for which there is no other warning to refer to it, those are unique. We call them unique. So this is a big part of the set. The other part, it's non-unique, and we were able to combine them into groups of warnings. So this suggests not a lot of overlap between the tools, but again, based on with the caveats of our analysis. Now, a different way to look at the tool overlap. Here we try to we look at first of all, for certain weakness types, what the number of tools that look for this weakness, and then average number of tools that report for a line with the weakness. So if there is a tool report for a particular line, then we look at how many tools report this line. Again, this is an approximation because it may undercount the overlap, because if you have, let's say, a tool may report at a different place. If you have a path, some tool may report earlier in the path, another tool may report later in the path, and this doesn't consider those cases. But the average number of tools per line with weakness is on the right, the scale is on the right, so this suggests not much overlap, because usually it goes from 1 to maybe 1.3, and it also depends on the weakness type. I guess in some cases more tools are looking for a particular weakness. This is just to point that how our evaluation was focused. So this describes only for the let's say, so by the security relevance categories, this describes the division into severity, the high severity warnings as reported by the tool, and the low severity warnings, severity 1, 2, and severity 3 to 5. And the other bar is the division, how many we evaluated versus how many we didn't look at all. So we tried to focus our analysis on the high security relevance categories. And for the medium and low, there is some that got evaluated for some reason. In some cases, it's just because they were associated with other weaknesses, as tools report weaknesses with different severity. So this is our analysis of the severity 1 and 2 weaknesses per test case. So this is the shaded parts are the ones that we evaluated, and the upper parts are those that we didn't look at. So in case of OpenNMS, again, it's a big test case, so we just gave up at some point. In other cases, I again ask you not to look too much into the true positive and false positive rates. I just want to suggest that, for example, for Lighty, there were a lot of false positives, but Lighty uses its own memory management routines, and they are fairly sophisticated, and the tools were confused. It was confusing to us to analyze the tool reports as well, as because this is a fairly complex analysis. Question?
Implemented in C, in which were implemented in Java.
Excuse me, can you repeat? So here the left three, name, Nagios, and Lighty are C programs, and the other three are Java programs. So now, just again, we want to see, can we trust our evaluation? So one of the participants, Grammatech, they commented, critiqued our evaluation, and we re-examined our analysis based on for those reports. So Grammatech reviewed about 100 false positives. We ignored one obvious case where we simply misunderstood the weakness name. And so they challenged our assessment, and so this bar, this pie chart originally in our original assessment, all of them were false positives. So after the re-evaluation, about a bit less than 2/3 were still false positives, and the other turned out to be true positives, but some of them were true positive but not security relevant. So I'm not, the yellow part, those are not such a big concern, but of course the red part, the 16, were true positives and security relevant. So this is a real problem in our analysis. And I also want to point out that we are not new to security. And so if it's so hard for us to to evaluate the weaknesses, it's also hard for the developers to analyze them. Now, lessons learned. So we got the XML reports from the tool makers. But in looking at this, we realized that tool interface is important to understand the weakness, at least for a more sophisticated analysis. Just the line numbers and weakness names, that's not enough information. We also learned that the simple binary true-false classification is not enough in many cases. You need, it's actually interesting that this may somewhat be affected by the perspective, and it also, there need to be the case, at least for the true but don't care type of stuff. The other problem that we often had was one tool may report one warning where another tool reports many warnings for the same weakness. And this depends on the paths that you have in code. So sometimes you may report many different paths, and it's not trivial to combine those weaknesses together, those warnings together. Sometimes also it's hard to say whether those are different warnings or really the same warning. And the tool reports are 6 months old, so tools are progressing rapidly. So this is, here we have a conflict. On the one hand, we would like to have a very careful study of the results. On the other hand, we would like to have a timely study. So once again, if I hope you don't miss this point that we want to emphasize not to use our analysis to rate or choose the tools. This was more of a study into how to do such a study than it turned out than to compare the tools. Some areas for improvements, definitely test selection criteria have to be clearer. The evaluation criteria have to be clear and as non-ambiguous as possible. We want to make it a community effort to involve others in this. Also, another thing is the communication with the tool makers. That's really important. We need to give them enough time to analyze the tool reports, because that can help the study a lot, and other things. So communication with tool makers is very important. And I'm asking, we would like to do another study like this in the future, so we want help in planning, choosing test cases, analyzing the tool reports. Finally, I want to thank several people. Bill Pugh had the idea for this, and he also helped with the output format, and he provided valuable critique as we went. SATE is modeled on another NIST study, the NIST text retrieval conference, which is ongoing, has been going on for many years. I want to thank people who did organization and analysis. Romain Gocher did a huge amount of work in all the aspects of this. Paul Black, my other colleagues at the NIST SAMATE project, experts from the MITRE team, especially Steve Christie. And most of all, I would like to thank tool makers for taking the risk to in participating in this study. This is not simple. And finally, this is my contact slide. So now questions, please.
Thanks. So I've got a question. At the beginning of the talk, you suggested that using the tools generates vulnerabilities fast. But don't you think that you should consider the validation time when you're thinking about using a tool? Oh, and sort of a follow-up question would be, how long do you think it would have taken you to validate all the tool results, if you had the luxury of all that time?
Steve Christie had a rough estimate that 1 year for 10,000 weaknesses. So we had 48,000 weaknesses. And so, of course, some part could be easily done faster. So I'm not saying that this is 5 years total, but this is a significant amount of work considering that Steve is an expert in this.
So some of the tools generated like 15,000 findings by themselves. So that would be 1.5 years, man-years, to evaluate those findings?
There are a lot of things involved here.
One thing that I think was really a big factor was that we were just going based on raw, simplified tool outputs using the XML format. We didn't have the live tool right there. In addition, while there was a lot of work done by Romain and Vadim in building up a database and a web browsing utility, I think the process of finding and tagging duplicates was a little bit slower than it could have been as well. That said, there were some cases where a tool might have reported, a backtrace of, 30 layers deep or something like that, and that could have taken me anywhere from, 15 minutes to an hour or something like that. Another factor, and I think this is just a general factor, is one of the main projects that I worked on was light HTTPD. And as Vadim mentioned, there was this very complex kind of memory management routines that were used all throughout the code. So those generated a huge amount of warnings. It took us some number of hours to really figure out what the routines were doing, how it was that they were working, and then to assess whether or not the tools had even gotten the results correct or not. So there's a good amount of sort of ramp-up time that's needed to even understand the application in the first place, which comes into play as a third-party evaluator, but which, the developer themselves wouldn't need that ramp-up time. So there were a few different factors there.
This is also somewhat of a misuse of the tool, this study, because a developer would normally look at the issue and think, should I fix it or not? And we are asking us a little bit different question. Is it a true issue or not? And what is the severity of the issue? So it may be affected by that as well.
Other questions?
So did you conduct a valid attack in order to say it's a true positive? Or did you conduct a valid attack in order to say this is a true positive or a false positive?
So he asked if you actually qualified false positive, the results to see if they were false positives or not.
Oh, so what's the methodology to validate whether it's a false positive or true positive? Yeah.
We did not run the test case. We did not produce a test case which shows that, let's say, the system fails in this particular case. So this is just a human review of the issues.
Thanks. I think the first question is, in terms of the selection of why you chose C and Java instead of C++ for either one of them, says a lot about perhaps the direct, well, in terms of like tangible use of the outcome of your study, perhaps? So have you ever, like, this is just perhaps like a suggestion or an idea. What you derive from there would show perhaps the number of, well, perhaps to bring out other than the weaknesses, but also the strengths of each kind of, you know, the specific programming languages that we are perhaps people within the industry would already know. But the thing is the integration of both in terms of deployment when it comes to limited resources, which you know, in a way emphasized. So do you see a direct, perhaps, application in terms of the deployment of the use of, you know, writing programs? Are there certain sections or functions which you find may be more effective written in C and then be able to integrate that with Java? Is that one of the, perhaps, the tangible outcomes that your team is looking at? Perhaps I'm more concerned with, like, you know, after going through the study and the research, you have a specific outcome. You have obviously very valuable findings. In terms of translating that into real, you know, how would that benefit the developer community is perhaps the question that I have.
It's a fairly loaded question, and those are important issues to consider. We don't have much. I guess it's kind of hard for me to really answer this. Yeah, I would be glad to talk about it in more detail, but it doesn't seem like I can tell it simply.
All right, so something that immediately strikes me every time we talk about vulnerabilities and consistency of tools is why in the world we don't have a consistent vulnerability definition. I think that should be the next big OWASP project, is let's consistently define what vulnerabilities are, what their risk categories are, what ratings are, and try to figure out a way to quantify that, because everybody talks about, you know, between tools manufacturers, right? We find more critical ones, but the definition is completely and utterly up to everybody else to interpret.
The MITRE people are working on this. Steve can tell.
Yeah, that was a great setup, stranger who I did not pay $20 to. The question that you bring up has also been brought up by people at NIST as well as Department of Homeland Security, which funds the CWE effort. So one of the things that they're hot on, which means we're now hot on it, is just like for real-world systems with applications, software installed on them that have vulnerabilities, where there's this CVSS, there's a notion of this common weakness security scoring. There are certain complexities that go beyond just, you know, you have this buffer overflow in this Microsoft software package. Context being a really big part of that. So, you know, how can you assess the general severity of a particular issue across, you know, all different kinds of threat models, for example, and deployment scenarios without taking into account certain kinds of context. So it's a really good question. We understand that it's something that a lot of people want. Anyone has any ideas or any criticisms or anything like that, I'm definitely around and receptive to that. That is something that we are going to be working on fairly heavily over the next 6 months to 3 years.
One of the quick things that I wanted to mention is I think that, as you're saying, CVSS and a combination of the CWE, I think is pretty good. Both of those two things, if you use them together, can kind of meet those goals, right? Yeah. Sure. Any other questions? No? Yeah, we have a comment. One more.
So just to add on to that last question, I wanted to point out that, you know, I think CWE is great and they're doing some really good work there. The OWASP project to build the application security desk reference, is also a useful project. It's going beyond just vulnerabilities or weaknesses, and also building reference materials for threats and attacks, and also, I mean, it also has vulnerabilities, but on the other side, it also has impacts, both technical and business impacts. So we're trying to provide that bigger context.
When you publish in December, do you swap to NIST website, or some way we can get plugged into when the results are published?
It will be on our website, SAMATE website. So from this site you can find it.
Any other questions?
How do you think, how reliable are the results, given that only like about 12% of the found vulnerabilities have been actually looked at? Couldn't, like, if all of them would have been taken into account, don't you think that would have changed the overall results of your findings?
There is a big error in this, in our analysis. So our analysis may only be useful as a way to describe the issues that we have. So it's more of a learning exercise for others if they do such a study later. And we will try to emphasize this as much as possible. The raw tool output is, of course, very useful for, maybe useful for researchers, but our analysis, it's more of a what not to do, what to do differently, maybe in some cases what to do right, but only a small part of it, really. I want to again emphasize that if there are issues, try to blame us, not the tool makers first, because if there is a problem, it's probably because we did not analyze it right.
I feel like the elephant in the room is that, well, who actually has taken the time to actually rack and stack these and objectively done quantitative analysis of these tools relative to each other? So I don't know if that question's been asked, but you know, Gartner has studies out there that are kind of qualitative. I've done some research myself in terms of that's fairly quantitative, but do you know of any research that we can look at to actually rack and stack these tools? Yeah, I mean, are you aware of any research that actually objectively or quantitatively compares the analysis and the results?
Yeah, it's our goal. It's our goal to make this much better. It's. Oh, you were asking about.
Is there anything currently out there today that?
There are several studies done by other people.
Are you going to publish the raw data so that if someone wanted to go finish the work that you started, you could complete the analysis and then use the data that you've already collected to rack and stack the tools?
Well, we are definitely going to publish the data from the tools, and our plan is to publish all the data, but we are now looking into how to do it so as to publish the right thing and not to publish our mistakes. But we are definitely, would love somebody else to complete this.
We have one of the challenges that has come up just in the past few days through talking with various participants is, and a big concern that we have is people misusing the data to come up with the wrong sort of conclusions, right? Especially given that the data is so noisy and it is so complete that we only have 12% coverage. So if, for example, we were to publish all the raw tool data plus our own incorrect conclusions, everyone knows what the first thing is that's going to happen, right? Everyone's going to go to the raw data, calculate some numbers, and go, oh, that tool is better using our bad data. So we're very sensitive to that. We don't want to encourage that in any sense. So now it poses a little bit of a challenge to us as to how much data do we publish and how do we publish it in a way that minimizes potential incorrect conclusions being used with it. So that's a challenge that we're going to be facing in the coming months up to December.
have another question here in the back.
Have you considered expanding this to also compare black box tools versus white box tools and see the differences?
Yes, we are very interested in doing. We could do another track in the future. We could do a track for black box tools, and this would definitely be interested to have this comparison too. What kind of things the black box tools find versus the white box tools? Yes.
Okay, I think that's all the time we have. If you have any additional questions, you can kind of come up to the stage and ask off to the side. So, thank you.
Thank you. Thank you.
We'll be getting started with the next talk in about 10 minutes, so you have an opportunity.